Okay, let's continue. So yesterday we saw how every of these strange shapes called polymatroids can be characterized in terms of the facets, and not only the polymatroid, but all the faces of the polymatroid can be characterized by intersection of different faces. Today we're going to try to prove it. In this second part, I included all the proofs of the theorem, but talks are not the best places to show proofs. I will just give a brief outline. It's some of them you can quickly figure out what's going on. So I won't spend too much time on the proofs, because it's anyway hard to follow general proofs during the presentation. However, I may try to show you for low dimensions, just to see what's going on, to visualize it. And then, just quick comment on the homeworks. I gave two problems. Did you have like problem solving them, or you didn't try? You tried hard, or you hardly tried? So here, how do you solve this one? It's actually totally equivalent to solving this one. Any idea? I know I'm standing between you and the barbecue, but to motivate you a little bit.
Just rename the parameters A union B to A.
No, that's okay. I'm pretty sure you can see it. But how do you prove that this is true? Use H, yeah. Use the definition that I showed yesterday. So it's basically, if you break up this mutual information into H of Y given XC minus H of Y given the two of them, the union, and then what do you need to add and subtract? Something that appears there. This is a good answer. Yeah, okay. So you have H of Y given XC minus H of Y given XC union A. Okay? That's the mutual information on the left. And what do we have on the right? We have mutual information of XL given and Y given XC. So how about subtracting H of Y given XC union L and adding the same thing? What do you get? Just minus and plus, and that's it. That's it. Because this one combined with this one is the first mutual information. This one combined with this one is the second. That's it. Now, okay. How about the second homework? That was related to the Gaussian capacity region for n users, for 3 users. What do you get?
When you want to maximize the rate for the user 1, let's say.
Okay, so this is the second one.
Okay, so if you want to maximize the rate for user 1, which is the first question, the code last, it's the intersection of the dominant region with F1. That's what you can achieve.
How does it show up here?
If you take the...
Okay, the first question is plot the capacity region. How many quantities do we really need to calculate?
The 10 equations.
Yeah, we have 7 equations, but here everything is symmetric. So we really have only 2 quantities. So one quantity is 1/2 log 1 plus P2 plus P3 divided by 1, which gives 1/2 log. It's enough to have P2 divided by 1. So it's 1 log 3, right? And the other one is 1/2 log 1 plus P2 divided by P1 plus 1, which is 1/2 log. We have here 2/3, 5/3. So these are the two quantities, and they correspond to this point, the smaller one, and this point, the bigger one. And because it's symmetric, you get everything, these two quantities. How about now the first question?
Yeah, I didn't do any computation, but it's just on the graph.
Where?
It's on the last.
Yes, the small one here. This one.
Yeah, and
This is the one in which what?
This is the maximum rate of R1.
Maximum rate of our R1. What is the other one?
The other one is the capacity, the dominant region.
Which one?
The dominant hexagon you have. Oh, you mean the second question?
Yeah, the second question.
The one in the back.
Okay. It might be true if we say smallest rate. I would have said smallest non-zero rate. Okay. If it's the smallest rate, it can be 0. It's the last one. Yeah, that's true. The smallest non-zero rate.
Okay, then it's F23, which is the.
As this spectrum, right? Which is the same size as the one in 0, but here we have a non-zero minimum rate of user 1. So that means user 1 is decoded first, while the other two are noise. And hence, we can write the characterization of these two regions. For R1 equal max, equal this. The region is R2 smaller than 1/2 log 5/3, and R3 the same thing. We have two inequalities here. And then their sum, what is their sum? Smaller equal then, what is the sum? 1 plus what? So remember, in this case,
P1 is the noise.
user 1 is noise, right?
Yes.
So it's, we have here P2 plus P3
Divided by
or
1.
P1 plus 1, which is basically 4 or
5.
3, that means 7/3. 1/2 log 7/3. That's the characterization of the smaller region. The bigger one,
The bigger one. So first R2 and R3 are noise.
for the bigger one, we're gonna have here 1/2 log the big one, 3. And here we're gonna have this, the big difference, the big sum of R2 and R3. So we must have 1/2 log 1 plus P2 plus P3, so that means 1/2 log 5. And that's the solution of the problem. Okay. So I wanted to introduce this because later on we'll see that, I will go quickly through that, but it's always, we have a combination, a Cartesian product of some region and some dominant phase. So here, the region is for R2 and 3, and the dominant phase of one-dimensional region is a point, and that's where R1 is maximum. Okay, let's continue now. So we stopped here. How to show that? No, actually we didn't discuss this. So yesterday we discussed that someone from you noticed that in order to have a intersection between the front facets, notice from the figure. So I was using some labels with F, if you remember. So we said that this is F3, this is F1, this is F2. What is this here? F23, yes. Etc. So this is 1, 3, this is 2, 3. What is in the middle?
F1.
It's F1, 2, 3. And how about this edge? What is this?
This is B.
So this is the intersection of the facet 1, 3, right? With the back facet called B2, right? So we use the labeling F1, 3 given 2, okay? And we discussed that in order to have an intersection between the facets, there must be subsets of each other. If we have two, one of the other. If we have more, then we need this telescopic sequence. So if for this intersection we have intersection of 1, 2, 3, 2, 3, and 3. So that means 3 is a subset of 2, 3 is a subset of 1, 2, 3. And it's always like this. We mentioned also that 2, 3, and 1 cannot have any facets, and 2, 3, and 1, 3 they cannot have because they are not included in each other. On the other hand, in order to have an intersection with the back facet, then their intersection must be M. So that's what we commented. Today we're going to prove it. We see it from this picture, but it's a 3D case. We have to prove it for higher dimensions. And then, what was the condition that back facets intersect? They always intersect. That's good. Yeah. They are like on the back. So it's related to the fact that we have to just set up the rates to 0. And so it's R10 is back facet 1, R20 is back facet 2, R1 and R2 equals 0 is back facet 1, 2. So that's, in this case, back facet 1, 2 is what?
Just R3.
Yeah, is the edge in which both are 0, this edge. Okay, good. So now I quickly go to this proof. This front facet intersection. So we claim that this intersection is not empty if and only if S1 is a subset of S2 or vice versa. How do we show it? If they are equal, it's straightforward. So we have to look only at these cases. And I quickly go here. So we can reindex the users. So we assume first that S1 is the smaller one, and we can or a subset of S2. So we can reindex the user such that S1 is all the users from 1 to k. So S1 has k elements, and S2 has L elements. Obviously, L has to be larger than k because we assume that. And then this rate could be defined like we say we use again this chain rule. So like we said we start with x1 y given everything up to m, and then we go x2, etc., etc. So we have all the rates indexed like this, and then that means that R is a vertex on the dominant phase because it has all this by the chain rule. If we just add up, we'll get this maximum rate. So you can see it from this equation. But also in general, we can prove that this is true. So this is just simply the chain rule of mutual information that we showed previously. And then for I equal k, we get easily this rate, that this is equal to mutual information between the set S1 and Y given the rest, and for L, the same thing, but for S2. And this just proves that this rate belongs to both. It must belong to, according to the definition of the front facet, it belongs to both. How about the other direction, the on-leaf direction? So now we assume that this is the case. R belongs to these two facets. And we have some sequence of equations. So we have to, if we want to go in detail, so this is, these two, they come from the definition of the front facet. So remember, for any set, must be satisfied this equation. And then here we also have to include into the game this subset for the dominant for the front facet. So we just put any set. Here we put the, sorry, not subset, intersection. So we put the intersection. And then we keep this the same. If we combine these two, it's really just, if you look at the sets, you just get the difference here of this. And then here is this fact that if we make the condition, in the condition you have smaller set, this is smaller set, S1 union S2 component, this is smaller set than the other ones, then the mutual information decreases. So it must decrease here. And then look, magically, what do we get at the end?
Yeah, the other one is included.
Which one?
I mean, it's okay. I mean, the second term is included in the first term, that's why it's equal. Oh, you
No, if we combine these two, we get exactly this. We combine these two, it's a chain rule, get this. What do we get? Magically. What do we have at the beginning?
Yes.
The same thing. How come? So it must be that all these fellas are equalities, right? And then observe E. So in E, what I said, if you decrease the set here, it must be greater or equal. So now we claim that because of beginning and end are equalities, this one must be called this. In which cases this is true? So there are two cases in which this can be true. It's either this difference is 0, so this vanishes, both will be 0. What does that mean? S1 difference S2 equals 0. That means that S1 is included into S2. Maybe I should drop even the, we assume the quality, but it's okay, it's true in general. And the other case is in which S1 complement equals S1 union S2 complement. When is this true? If S2 is inside S1. So in that case, S1 union S2 equals exactly S1. And that's what we needed to prove the other direction. So now, we prove the condition for, just remind you again, for intersection of front faces. So, and this works for any dimension. It's not just by observing the figure here. So now what do we need? We need to see how the front and back faces intersect. This is auxiliary lemma that is, it's not that hard to prove. So it's basically claiming that that RL, it's in between this quantity and this quantity. So these quantities are similar, but except in the conditioning we have S here, different from LC. So it's basically, if you can you can look in the picture what's going on. So it's the L who belongs to, if you're on the front facet, you are between some of these two rates, and it's really, so this one it's always true because it's part of R. We said we can look at the second equation there. So we said for any subset of M, so L is also a subset of M, and then this inequality, we're just gonna play a little bit with these chain rules, and we can break this up into two quantities, because we can split S into L and S difference L, and then this one is true since we are on the facet, and then here we can use the same thing for another set as difference L here, and then at the end we use just chain rule, and we get this in the first.
Equality holds when you decode L first and L last. That's the two points.
Yes. Yes. Yes.
Decoding order.
It is the decoding order, exactly. And now I'm ready to claim this. What we observed in the 3D case, that there is an intersection between a front facet and a back facet only if and only if these two sets do not share any elements. Their intersection is empty set. And again, quickly, like to be complete for A equal empty set, then it's obvious, because remember, what was B empty set here? It's the whole thing. Yeah. So in that case, it's true. And let's say for a non-empty set, imagine R belongs to that such type of intersection, and then we start from 0. And then we go like this. Why is this true? 0 equal RA.
Definition back.
It's a back facet, so all the indices in A, all the rays with indices in A are vanishing, 0. And then we continue with this, and then we get this mutual information. So it means 0 has to be larger than some mutual information. Of course, equality must follow. And since we assume this non-degenerated, I just have to remind you, this non-degenerated condition is very important. Then we cannot have such mutual information that is 0. No mutual information is 0 actually, because it's non-degenerate, like in the Gaussian case. So it must be that this must be 0. In order to have this mutual information 0, we must have 0 here. It's like empty set with intersection KMS. The other direction, now we assume that there is no common elements between A and S, and then we pick a rate some R tilde in the front facing that is labeled by the same S, and let some rate R be obtained by this R tilde by setting to 0 all these coordinates that are in A. So in that case, R will belong to A because we set up all those coordinates, but also R belongs to Fs because these rates are equal. And we didn't change anything by setting up to 0 this element. So this is like, now we show two building blocks on how to show these intersections in any dimension, like on front facets and on front facets with the back facet. Earlier, someone from you immediately noticed, and probably all of you, that all the back facets intersect anyway. And now we just need to extend. So these are very, very important. We can extend to multiple intersections. These were only between two faces. Now we can add more and more faces. How many back facets are intersected with the dominant face? 0, right? Yeah, we cannot have, exactly because of this claim. In the dominant face, we have M in the entire set here. So, sorry, but they can't reach. Okay, and now we want to extend this thing to more intersection of more faces. So we claim that if we intersect M front facets with how many back faces here?
A. The whole set A.
What?
A back faces.
Almost. Cardinality of 8. Okay. So we have here. If we have 5 elements, we have intersection of 5 back faces. So that means this intersection is not empty if and only if the following two conditions are satisfied. First of all, this sequence is telescopic, so we can find a permutation in which every set in this is included into one each other. We may also make a convention in which we never label this face. We can always put the smaller set in, but I just want to be general this way. I complicate a little bit the things here with the permutations. So we just see that everyone here, they have to be included in the other, in the other, in the other until the end. And then, on top of that, this is enough. I mean, if A is not intersected with the first one, then will not intersect with So this is the condition. What is the dimension of such a face? So now it's clear that this is a face, right? It's a face obtained in an intersection of M facets and cardinality of M front facets and cardinality of A back facets. What is the dimension?
Big M minus small m minus cardinality.
Exactly. So the dimension of this face is big M minus small m minus the cardinality of A. Okay. And probably it's not that fun now to go to the proof. So it's again we have it's a very similar proof to the previous part. So we use this previous lemma. If it works for 2, it must work by adding more and more. So it's very similar. And then for the converse, if any of this Si is not contained in the next Sj, then immediately we get this. We are out of the game because our lemma is not fulfilled. So they don't intersect. And the same thing here. On the contrary, if this happens to have a common element with A, then we're immediately out of lemma 4. So that's why we must have fulfilled all these lemma. Okay, now we go to the most interesting animal called dominant face. And people in information theory like to call it dominant face. I wanted to ask you here something. Okay, let me just state the things that are written. So, as we noticed, it does not intersect with any back face. I will repeat this, and then, okay, one user case. The dominant face is a vertex. It's the maximal point in the regions because the one user case is a line. It's a segment. In the 2-user case, we saw this pentagon. It's an edge. In the 3-user case, is this hexagon. and so on. And we'll see later on how it develops. This is interesting. I showed you this telescopic sequence. So we start from the smaller set, and then we go. So from the biggest set, and then we go. All of them, they must be included with each other. So here, as we say, let's say we want to characterize certain vertex, as we said, 1, 2, 3, and then 2, 3, and then 3. Which, what is this? It's a vertex, right? Which vertex? This one, right? What is the decoding coordinate to this vertex?
1, 2, 3. We decode 1.
The decoding order. So first we decode 1,
And then 2.
and then we decode 2, and then we decode 3. So what do you observe? How does this compare to this intersection?
Each time we decode the...
It's just we have some differences. So difference between this and this set gives us 1, and difference between this and this gives 2, and then the last one is 3. So that's the order. The decoding order is given by this this sequence of decrements, and we can use either way to label the vertices. And this sequence gives the order. We can have, of course, there are more complicated things. We don't need, in this case, because we get a vertex, the decrements are always sets of size 1. We can have a set of size 4, and then set of size 2, and then set of size 1. So between 4 and 2, we'll have 2. And in that case, we don't have a vertex, we have edge. But again, it's a decoding order in which first you decode jointly 2 users, and then another user, and then another user. So it can be generalized for any size of set. And this is what, yes?
So before we go in now in class, can I ask a question? More bigger picture question. Let's ignore Gaussian for a minute.
Yes.
Then the capacitor is a union of these.
Yes.
And that is much less structured than these.
Of course, of course.
And so what insights from this analysis can you take back to the capacitor?
I don't see it immediately. Yeah, it was
Mainly only for the Gaussian.
exactly. We tried to characterize the Gaussian region, and if you want a particular, so that's why I want to point out this. I write here C and I write here R.
Yeah, I know. I mean,
So-
you're doing the basic object, but when you take unions, you lose. all
No.
the-
You totally. You lose. I mean, you will. It will be like throwing everything into the sea, and then you got. It's just to see the structure for this for the polymatroids, if you want. Like, can read the mathematical problem like for determining all these phases. Okay, and yesterday we mentioned, and many people know that on the dominant phase there is a permutation set of M, and then we get this factorial. What is this? How many vertices do we have?
You have some intersection from the back.
It's probably the dominant phase of force.
As the dominant phase in 4D, exactly. The dominant phase in 4D. For what 4D plane? Yeah, it's actually for the case when the rate is maximum. So is actually we have the coordinate of the fourth user equal to this maximum mutual information minus the 3. So it's that. And how many vertices do we have here? Should be easy.
24.
4 factorial, 24, yeah. How many edges? It's not that easy, so. You will see later in the lecture. It's going to become easy. Okay, same factorial, m minus 1 divided by 2, something like that. We'll see later. So it means like 36. Okay. And now is the fun part of everything. So we build up this theory and formal proofs. And now let's see how we can count the faces in any dimension. So faces of any dimension within the capacity region of any dimension. Obviously, these d-dimensional faces we limit between 0 and m. So for d equals 0, it's a vertex. For d equal m is the entire region, so it's always 1. And then we built the proofs on counting first the number of front faces, and then the number of back faces. And then, obviously, the sum of the front faces and the back faces will give us the total number of faces. And then, this is going to be fun. We get a closed form expression for the special cases for 0 and 1, for d equals 0 and d equals 1. And this is the solution. We start from the number of d-dimensional faces on the dominant face of R. And then we will see how it develops. Does anyone have an idea what is this? It's m factorial. Why?
Well, actually, you are choosing function and it's really loud and doing.
Okay, that's good. So if you set up d to 0 here, you will get that equation, and that will give you m factorial, which is the number of vertices on the dominant face. How do we prove this? Actually, I was using partitioning of a set more like, and the proof is very, very interesting. You will see it now. So we start from this f with all the indices, the entire set, and then we go from S2 to some Sm minus d, and this has dimension d. So we have, and this is the dominant face, we don't have any back faces. And then these different sets, like starting from m minus S2, and then S2 minus S3, and then we continue till the end, in which the last one is Sm minus d, if you want, minus the empty set. These, they form m minus d partition of m. Are you familiar with partition? What is partition? Yeah?
So M subgroups the M, D subgroup and M that they don't intersect.
Partition is actually, you have a set of m elements, and then you wanna know how many different ways are to partition this set into m parts. So let's say, how many ways are there to partition this into 2 parts? How many ways are there to partition into 1 part? If it's only 1. How many ways are there to partition in m parts? There is 1. Well, just you have 1. How many ways are there to partition into 2? M choose 2, etc. How many ways there are to partition into 3? So you get this multinomial formula. You are all familiar with the binomial coefficient. Here you have a multinomial coefficient, and that's the answer. And it's related to a number called Stirling number of the second type. So Stirling number of the second type gives you the number of partitions. And how do we get there? We start with what I call this multinomial coefficient. So in the binomial coefficient, you have here only 2. And the most common notation is to put only one of them. So we never say 5 factorial, we never say 5 choose 2 and 3, but we say 5 choose 2. But when you have more, it's you put all of them. So here we have m minus d elements into this, and this is the equation. So you need to have products of all the factorials into this sets, and then you have to change them. You have to change them from 1 to such that their sum is always n. And then, again, you are generalizing the binomial formula, which is a plus b to power of n, is all of you are familiar. We are generalizing to a polynomial formula, and then we get such expression. It's not difficult to get this. It's just for each x we have this coefficient. And then, actually, this quantity multiplied by m factorial will give you the number of ordered partitions in our set. So actually, the number of d phases into dimension m on the dominant phase is pretty much the coefficient of this expansion, which I showed before, in front of x to the power of n. So we need only the what coefficient do we have in front of x to the n. So don't forget here we have like power. It's not trivial. And then look here. We can just continue to infinity. It will not change the n coefficient. And what is this? Exponential. It's e to the x, exponential to the x. So it's a very, you're getting a very condensed expression. And so we say coefficient in front of ex minus 1 to the power of m minus d in front of this mth power. And according to the Taylor formula, as the nth derivative. So the nth derivative of this power m minus d, but evaluated at 0. Because we need to have
To get rid of the others.
the coefficient. Yes. It's actually Taylor series expansion at 0, of course. It's equal to 0. And now, how to find this derivative? So I tried hard, closed form expression, forget it because it explodes, and I got this some result. So this one, for this one, we use the binomial formula now. So this one goes to e to the x goes to power of j, and the minus 1 goes to power of m minus d minus j. And then we have to take m derivative, so we do it for the sum is conversion, we do it for every term of the sum. And then we get this one. It's easy because we have only to derive here in e to the jx, and then that's why we get j to the m, because we have m derivative. And now we have to set up x equals 0. So this will vanish, and then we get the result of the proposition. This one. So this gives us number of any d phase, number of any d phases on the dominant phase in a sum form. And now we continue further. So now we say, okay, we have the number of phases on the dominant phase. How can we use it to find the number of front faces, all the front faces. So up to now we were here, finding all the faces here. So now we want to include these chunks here on the front. It's very interesting. It's related to this recursive formula. So it's equal to the number of faces on the dominant face plus the number of faces of lower dimension. And it's because of the fact that if you go in the back, you're reaching easily to a dominant face of a smaller dimension. So if you go here, from this spot here, you have a two-dimensional region, and you're on the dominant face. If you continue, if you go there, you have one-dimensional region, you're on the dominant face. And magically, everything is dominant face, except the origin. So the origin is the last point at the end, the last vertex where we come. So this is the next proposition to show that this is true. And I will skip this because it's this is what I say is any d-dimensional front dominant face is some dominant face for. So as I said, we have only dominant faces, and we use this recursion formula, and then we develop further. What is the total number? Okay, here maybe I can make a little intermezzo. So this is the Stirling number, and we have this notation. Maybe some of you saw it. Instead of using for the binomial coefficient the normal parentheses, we use the braces. Some authors call it Karamata notation, and so this really means to partition the set number of partitions in the set of m elements. How many n partitions are in there? And then our results can be written in the following form. If this is the case, so we have m minus d partition on the set n, so the number of these partitions, multiplied by the m minus d factorial. This is the Karamata notation. There is also one thing that's called binomial transform there, which is defined by this. So if you use this binomial transform, then this is the expression for the number of d faces on the dominant face. You have to multiply by this minus 1 to the m minus d, and then you have the binomial transform of size m minus d of k to power factor. So it's just a fun way of compact way of expressing. So now we want to count the d-dimensional back faces, and it's again an interesting formula that I mentioned a little bit earlier. That any back face is front face in a lower dimension. So when we start from m and then we go to lower dimension, the first back face is at dimension m minus 1, and then we have m minus 1 such m choose m minus 1 such dominant faces, like in this case will be 3, and then we go further. We lower the dimension, m minus 2, m minus 3, and then we'll have to stop at d, because d is the dimension of the face. If we want to go for the vertices, we put 0 here, and then we start at 0. So this is the total number of back faces. And as you mentioned before, this is the dimension. What I asked before. So I'll skip the proof again. This proof is really not good. Just deals with the cardinal. It's very easy. So now this is the fundamental result, the main result of the whole talk. This is the total number of faces in the capacity region. Okay, in the capacity region of the Gaussian, or in the region of particular region R. And how do we get it? We just use the previous two. We combine the total number of faces with the number of front faces plus the number of back faces, and then is basically, you notice the number of back faces goes up to m minus 1. And as I said before, I just add the last one to sum up to m. So we really, what I said before, we really get that everything is front face somehow, like except the origin for d equals 0. And this result is straightforward that we get from the we replace what we got at the beginning, this sum that I showed you, similar to that. So you just need to write it for d and write it for d minus 1, and then you do some combination.
Is there no other way to simplify this?
Is what?
You try, is there any simpler expression of this? Because it's, I mean, can you simplify the final result in a different way? Can you express it a different way? Because
Maybe, I don't know. Maybe. I was trying, I couldn't find a better way, but maybe.
it seems.
And then, if I write it into this shape, I really have to argue about this, that if the dimensions and the dominant face are equal, then this is 0. And if you take 1 less, it's 1. And by convention, we get minus 1. This ND of any I minus 1 is 0. So this is just repetition of the previous results. Just to complete. Okay. So this concluded the main result. So we managed to calculate the number of any phase in the dominant phase and the number of any phase of any dimension in the entire capacity region. And we discussed that we can also count the front faces, the back faces, etc. So now, what is the result for d equals 0 in the capacity region? So we said before, yesterday we discussed this, for n equal to, number of vertices is 5, right? Because we get this term. And E times 2 factorial floor equals floor of 5.42 equal 5. What is for m equal 3? So it's 2.71 times 6. This is 16. So we can calculate, and it's interesting for any m. It's just this simple number, e times n factorial floor.
How did you come with it?
You'll see.
N factorial by plus n factorial by 1 factorial plus n factorial by 2 factorial. That's it. Up to n factorial. You can write it alternatively as just n factorial plus n factorial by 1 factorial. Expand e as 1 plus 1 over.
You can do.
And
Yeah.
then just you get the integer
Yes,
very
yes,
cleanly and
yes,
see where
yes,
this comes from.
yes.
How it comes.
Yes. So this is the proof. Actually, I used this notation ND I0, so that means vertex in any of the dimensions, starting from 0 to n. And then, because this is a dominant phase, and we know that the number of vertices on the dominant phase is I factorial, that we proved that before. So we don't need to use that complicated formula, we use the simple formula, the one over there. So we just replace this by I factorial. And then, what do we have here? We just, I factorial goes out, and then we have this one, which is equivalent to this one. We can change the indices here. And what is this? We write it a little bit different. We put everything up to the infinity, and then we subtract from n plus 1 to infinity. So this is 1. And then this one, what is this? This is the Taylor of e to the 1. So we can immediately recognize it. So it's just this constant e times m factorial. And then we have minus this complicated part here. So now we try to bound it. We have to bound it a little bit, and then we'll see that. So this one is equivalent to this. So we just add the m, and then we start counting from 1. And then this one is a product of all of this from 1 to I. And then we take the smaller one, such that to have to bound it from above. And then it's really like a geometric progression. We can have it closed form. So this one equals 1 over m. That one is strictly smaller than 1 over m. This is true for all non-zero m. And this is okay, smaller equal than 1, but the m equal 1 is a trivial case, so it's smaller than 1.
That's why you take the floor.
And then that's why you take the floor. So it's basically we have this plus something that is smaller than 1. We take the floor and we get into this. So that's how we got the total number of vertices. So this is for some of them, to see how it develops. Like, for the dominant phase was m factorial. For the total capacity region is e multiplied by m factorial, and then you take the floor. If we try to do some Stirling approximation, which is not very important here, but just to use it for the factorial, for this approximate formula, then for big M we can get and see how it behaves. So it's like this. What is the number of vertices of a hypercube of dimension m? Two to the m. So we pretty much get a line here in the log space, and of course that line will be smaller than this because this exponential is not small. And then we can do it in closed form for total number of edges. This equals m half multiplied by this. For the two-dimensional faces, it's a bit more complicated, so I couldn't calculate in general for everything in such a compact form. But it's another homework. Maybe let's try it. And this is somehow a table in which you see all the results in closed form. So we start from the dimension m. We have only one region, and we have 0 such in the dominant phase. This is the number of facets that we discussed. M back facets, 2m minus 1 front facets. How many facets are on the dominant phase? Only one is the dominant phase itself. dm minus 2, d equals m minus 2. We get a little bit more complicated. It's interesting this one to notice it comes from the fact that this Karamat annotation for n for m minus 2 equals m choose 2 actually. Did I read it correctly? No, sorry. And then I write here the compact notation for using this Karamat notation for this general result. Any like number of faces of any dimension in the region. This is number of faces of any dimension on the dominant phase. And these are the two homeworks. This is the one that I showed before. This is the easy one. And this is the edges that we commented yesterday. That I asked how many edges are over there. So it's for m equal 3, this 3 factorial. And and this is
Yeah, it was 6.
okay. And what did I say? I said 24. Probably I was thinking from that.
No, for 4, you said 4.
Ah, yeah, exactly. Yeah. Sorry. Yeah, we were commenting for 4, so this is 24. It's 36. Yeah, that's what we said. That's good. Good. Okay, this is. I chose this way to show it, so you can see this number NMD, total number of faces for any dimension, and then you see when it finishes, that's the dimension. So this is for m equal 20, m equal 19, and then for m equal 20, this is there is one capacity region, and then you go further. Several of less, should be something here. What do you see? M plus 2, m minus 1 vertices, and it's 20 plus 2 to the 20 minus 1 facets. But we have to take logarithm. And then we lower the dimension, and this is the number of vertices. 20, 19, 18. That's how you read this. I like it because you can put more information on one page.
Can you just go back to the table response? My question is that each vertex in the dominant phase corresponds to order of decoding. Each vertex in the dominant phase corresponds to order of decoding.
Yes.
So that's why in fact now one might expect some symmetry in terms of degree of the vertex, the degree of the vertex, number of edges coming out of the vertex. But that seems to be lost because when m is even, m minus 1 over 2 doesn't divide in finite. So that's not teacher. I'm trying to figure out why there's an average. So if you divide the edges and divide by the vertices, you get m minus 1 by 2 on average. But m minus 1 over 2 is not a number when m is even. So you understand what my question? The vertices are kind of symmetrical, but somehow when you count, so you expect the degree of the vertices to be constant. It's true for 3, but not true for maybe 2 or 4. And there's a lack of symmetry. So I'm trying to count which commutations have edges between them, which don't have edges between them. You understand why?
Yeah, I cannot answer it now from top of my head, but maybe related to the fact that you cannot jump in
No, I
between.
want to see which commutations have edges between them. There's some relation between.
How about looking at this?
Yeah, so the top face you can see, but I want to see which 4, 2, 4, 1, 2, 3. There's some story there which I can't figure out yet. Which commutations have edges between them?
Because not all of them are. So you really have to see if you observe this and this. Then there is only one flip. This is flipped. 1, 4, 4, 1. If you observe this and this, one flip again. Actually, 3 and 2 are flipped. So it's always this neighboring vertices that are connected by an edge.
No, but if I think that's it may have to do with cyclostructure. I mean, maybe just but it's not just a neighboring flip because then the count is not correct. Maybe a bit different because look at the top 4, 1, 2 and 1, 4, 2 and there's 4, 1, 2, 3 and 1, 4, 2, 3 and 1, 4, 2, 3.
Yeah, you just flip 4 and 1, right?
No, 4, 2, 1, 3. And you just so then it becomes a bit 1 and 2.
Oh yeah, no, but 4, 3 are fixed, and then you flip 2 and 1. So it's like it's a circle.
Any kind of
Yeah, so it's you flip only 2, but see like this. You said about this.
Okay.
4 and 3 are fixed, and then this. Yeah. So it's always like this. It's like I don't know, like in this Hamming cube, you change only one thing. So here you change only the ordering. It's related to the structure, to this submodularity or whatever. So this set of increments that I showed you before. So if you observe, this is true for all of these 24 vertices here. Okay, how much time do you have? 15 minutes. Maybe I can slowly conclude with the last part. The hard one. Okay, now up until now we talked about the structure, just counting these faces, characterizing, showing why do they intersect, and then now we wanna add a bit flavor. How is this related to successive decoding, which I call group successive decoding, because you don't need necessarily to decode user by user, but you can decode groups of users and then decode them jointly, or again successively. And then I just want that you remember this one, that each phase is a Cartesian product of regions and dominant phases of region. So that's it. So for each phase we can say that. And then the rates on this intersection of these phases are done by this group successive decoding. If you remember this, I'm very happy. And then, okay, we introduce some, again, the original channel labeled by WY, this is the output. Whatever we put here is the output of the channel, whatever we put here is the input in the conditional probability. So don't be confused. I want to use this W because to represent the channel. And I use P for the input distribution, so that is the probability for all the users. So here, for any two sets that are inside M, if they don't intersect, we can have channel with inputs in U and outputs Y and X V. So this is, in the successive decoding, you may imagine that this is given, already decoded, and the transmitter, the receiver knows. Is stripped, the part that is stripped. So again, this is the output, this is the input. So, and then we can develop it. We can use these chain rules for probability and get some structure to these chain rules. And now, a rate tuple for this region, we define it by RU, because a rate tuple is defined for the input. What are the achievable rates for the users that sit in this subset U? And according to what we discussed before, it's just the same set of inequality, but this L has to be subset of U, and then we have here, we said that V is given, so that's why we have to condition on not only on this L component, but it's V union U minus L. And then the dimensionality of this region is exactly the cardinality of U. So how many users, that's the dimensionality of the region. The dominant phase of this region is obvious. I mean, on top of this, we just add the final equality. Like in that case, the dominant phase will be the region R that I showed here, plus we need one more equality, which is I of x1, x2, x3, and y, or sorry, R1 plus R2 plus R3 equals I of x1, x2, x3, and y, just to be on the dominant phase. So we need, on top of this sets of inequalities, we add one more equality for all the indices in the set U. By this we define two animals. So one is called the region, and one is called the dominant phase of the region for this channel. with inputs in U and output Y and all the other users. V. And we have 4 such similar regions. So again, here we have a region with inputs S and the outputs, everything that is out of S plus the regular output. We have dominant phase of that region, plus we have this region in V. We don't care about the other users, but we care about S. And we have the region, we have the dominant phase. So here it corresponds to what was the homework action. The party that is up is the bigger pentagon. The party down is the smaller pentagon. What is the dominant phase? What are the dominant phases of this? So the pentagons are R's. What are the D's? So it's either this or this. And every phase can be characterized in terms of these 4 regions if we start changing those S sets S. And it's pretty elegant. Like, just define it and then you can change. So you notice that this is exactly equal to this, but we add only one more equality. This is exactly equal to this, but we add this additional equality to define it. And then we want to prove that all the rays belonging to a certain phase is equivalent to this rate of the complement set belonging to the region defined by this input, XSC, and the rate Rs is in the dominant phase. So that's very elegant. So one party of the users belonging to the dominant phase, the other party belonging to a full region of a smaller dimension, which was what we discussed here. So one is belonging to the dominant phase. This is dominant phase in dimension 1, is the vertex. And the other are belonging to a full region of a lower dimension. And you can do it for any phase. Any phase of any dimension. You can just write it in such a shape. And the proof is not really complicated. It's based on the definitions of these R's and D's, which are really simple. And we are pretty much coming to the end, so I'm not going to spend time on the proof. I just wanted to explain it on the 3-dimensional region, so it's obvious for you to visualize it, but it's valid for. You have to believe me, it's valid for. The proof is there. And the dimension for this facet, of course, we know that the dimension for a facet is m-1, but then the dimension of this is the dimension of this region plus the dimension of this dominant phase, and this is dimension of this is we set SC because this is the cardinality of SC because this is set SC, and then the cardinality of S, but don't forget this is dominant phase, so we have to take out 1. So this is because cardinality of SC plus cardinality of S is. And then the decoding order is this one. So we have one group called SC, we decode it, and then given that, we decode the other one. And that's why that party has bigger rates on the dominant phase. But generalized, like for any general division of the set M. And you can generalize this Cartesian product. So if again you have this telescopic sequence, SM is a subset of SM minus 1 up to S1. we have that the small one belongs to this channel, and then for any eye, these increments belong to some dominant faces, and smaller dominant faces. And this is cool. It's always rigid, and plenty of dominant faces in the lower dimension. And the proof is, again, it follows the previous proof. So you just have to do it for every of these increments, but it's just a matter of notation here. What using the dominant. There is a converse file, which is even easier. What I want to see, the dimension. This is interesting. The dimension of such a face. We discussed it before. It's m minus m small lowercase m. We don't have back faces here. It's basically the dimension of the first region, the small one, the little one that is decoded first, and all these dimensions of the dominant faces in between from I1 to M. And this is M minus S1, and then you add this, plus this, minus this, plus this, and at the end you finish up with M minus M.
But you can also view this as each SI introduces the quality constraint. So your ME quality constraints, your RN, so your
That's true. That's true. Yeah, it's more simple. Yeah, I agree. I just wanted to make a point that okay, you start with always with one region and M dominant faces in some lower dimension. And this is the decoding point. We start with the S1C, and then it's all these increments. The difference between S1, S2, S2, S3, and up to the last one is the set SM. And now a corollary just to take care about the really all the faces, also the ones that are on the back. And there, the dimension is just, we have to lower by 1 to 8. And it's again the same principle. So this belongs to this back face. We start from the same thing, and then we have all the decrements. And just, this is the difference. These rates in back faces. But don't forget the dimension is small here because of the back face. And then, again, the decoding order, here you have to take out the A, the 1 square 0. And then you do the same thing. So that's pretty much it. Muito obrigado. Questions? I wish you a good barbecue.